Have you ever wondered why water boils at 100 degrees Celsius, but the rubbing alcohol in your bathroom just seems to vanish right off your skin? I mean, they're both clear liquids, but they act completely differently. Well, the answer is hidden in these invisible forces that basically hold our entire world together. And in this explainer, we're going to make them visible. It all kicks off with something you've probably noticed. You put rubbing alcohol on your skin, and it feels cold, right? That cold feeling is actually the alcohol evaporating like crazy, pulling heat from your body as it makes a quick escape into the air. Water, though, it just kind of sits there. So the real question is, why? Why is one so desperate to leave while the other wants to stick around? So what even is a boiling point? It's not just some random number. Think of it as the temperature where molecules get enough energy to hit escape velocity. See, to break free from the liquid, a molecule has to fight against the stickiness of all its neighbors. And the stronger that stickiness, the more heat you've got to pump in to help it make that jump. Now, that stickiness has a proper scientific name: intermolecular forces. These are the attractions that exist between all the separate molecules. And to really, truly understand boiling, we have to understand these forces. I like to think of it like a video game. We're going to level up, starting with the weakest force and working our way to the most powerful one. So let's start climbing that ladder of intermolecular forces, starting right at the bottom, with the weakest of them all. Okay, so level 1. This is the most fundamental force there is. It's the one that every single molecule in the universe experiences. We're talking about London dispersion forces. You can just think of this as our baseline level of attraction. So how in the world does this work? Well, imagine the cloud of electrons whizzing around a molecule is constantly shifting, kind of sloshing back and forth. For just a tiny fraction of a second, you might get more electrons on one side than the other. This creates a really weak, temporary little magnet. It's like a fleeting bit of static clinger. And that can cause a chain reaction in a neighboring molecule, and for that one split second, they attract. Now, it's weak, for sure, but it really adds up, especially when molecules have a lot of surface area to work with. To really see this in action, let's check out two molecules that are isomers. All that means is they have the exact same chemical formula, in this case, 5 carbons and 12 hydrogens, but they're just built differently in 3D space. First up, we've got pentane, which is basically a long, noodly chain. And second, we have 2,2-dimethylpropane, which is all bunched up into a tight, almost perfect little ball. Now, this is where things get really cool. The only force that really matters for both of these molecules is that weak London dispersion force. But look at the numbers. The long-chain pentane boils at 36.1 degrees Celsius, while the little compact ball boils at just 9.5 degrees. That is a huge difference. And it's all because that long chain has way more surface area, giving that static cling more places to grab on. This analogy just nails it. The long pentane molecules are like flat sheets of paper. They can stack up really nicely and get a lot of contact. The compact molecules, they're like crumpled up paper balls. They only touch at a few random points, which makes them way easier to pull apart and send flying off into a gas. All right, time to level up. What happens if that temporary, fleeting attraction we just talked about becomes, well, permanent? Then you get a much, much stronger attraction: dipole-dipole forces. This happens in what scientists call polar molecules. It just means the electrons inside aren't shared evenly between the atoms. This creates a permanent, slightly positive end of the molecule and a permanent, slightly negative end. So instead of a quick flash of static cling, these molecules act like tiny little magnets, always trying to line up and stick to each other. Just look at the difference this makes. Isobutylene and acetone have almost the exact same mass and shape, but acetone is polar and isobutylene is not. The effect on the boiling point is just staggering. Acetone boils at 56 degrees Celsius, while its nonpolar twin boils at a frosty negative 6.9 degrees. Adding that permanent magnetic pull makes a massive, massive difference. Okay, now for the final level up. This is the boss battle of intermolecular forces. It's a special, supercharged version of that dipole-dipole force, and it's the reason water is so unique. This is the hydrogen bond. So what makes this a superbond? Well, it's this extremely powerful attraction that only forms under very specific circumstances. You need a hydrogen atom bonded directly to a really electron-hungry atom. We're talking oxygen, nitrogen, or fluorine. These atoms are so greedy for electrons that they make the hydrogen intensely positive, which lets it form an incredibly strong link with a nearby molecule. And this is the absolute perfect demonstration. Dimethyl ether and ethanol are isomers. Same exact atoms, same exact mass. But in ethanol, you've got a hydrogen attached to an oxygen. That means it can form hydrogen bonds. Dimethyl ether doesn't have that. The result? Ethanol boils at 78.4 degrees Celsius, while dimethyl ether boils way, way down at minus 24.8. Just let that sink in for a second. That's a difference of over 100 degrees Celsius. The only thing that separates these two molecules is the ability to form this one special bond. That is the incredible power of the hydrogen bond. Okay, so the rules for boiling seem pretty clear, right? Stronger forces and more surface area equals a higher boiling point. Simple. But what happens when we're melting a solid into a liquid? Does the same logic actually work? Well, get ready for a pretty big plot twist. So yeah, just to recap our logic for boiling, it's all about beating that intermolecular stickiness. More surface area for the weak forces, or the stronger pulls from dipoles and hydrogen bonds, it all means you need more heat to break those molecules apart and let them fly free. See, melting is a totally different game. You aren't trying to completely separate the molecules from each other, you're just trying to break them out of their perfect, rigid crystal formation and let them start sliding past one another. So does our simple stronger equals higher rule still apply here? Let's bring back our old buddies, the pentane isomers. Now remember, the long noodly one had the much higher boiling point because of all its surface area. But look at this. For melting, the trend completely flips on its head. The compact ball-shaped molecule has a ridiculously higher melting point, over 100 degrees higher. So what on earth is going on? And here is the twist. For melting, it's not just about how strong the forces are, it's also about how well the molecules can pack together into a solid crystal. The supersymmetrical ball-like shape of 2,2-dimethylpropane lets it pack into a really neat, tight crystal structure, kind of like stacking bricks. The floppy, awkward shape of pentane just can't pack together that well, and it takes a whole lot more energy to break apart that beautifully ordered crystal, which gives it a much higher melting point. When it all comes down to it, what we're really talking about is one of the most fundamental rules in all of science. Structure determines function. The specific 3D shape of a molecule dictates literally everything about how it's going to behave. So let's wrap up with our key takeaway, the power ranking of these forces. At the very bottom, you've got the universal but very shape-dependent London dispersion forces. Taking a big step up from there gives you the permanent magnetic pole of dipole-dipole forces, and then, at the very top of the mountain, you have the supercharged hydrogen bond. These are the invisible forces that control the physical world all around us. So we've seen that for a molecule, its 3D structure really is its destiny. It determines if it's a gas, a liquid, or how it stacks up as a solid. The last thought I'll leave you with is this. What else in our world, from the proteins that make up our bodies to the very buildings in our cities, follows that exact same rule?